Okay, so your question today is how can I rationalize a denominator? That's a great question. I'm glad you asked it. And also keep in mind, you have seen this before. This isn't new. We're just in a section that's really focusing on radicals, so we're talking about it again. You have definitely seen this before. Okay, so first let's kind of go over some terminology and words. So an expression involving a radical with index n is in simplest form when these three conditions are met. Now, so the reason why I'm talking about this is you might see something where the directions are simplify, and it's a radical. These are the things you need to make sure are met in order to satisfy that. So first one, no radicands have perfect nth powers as factors other than 1. All this means is, can you break down the whatever radicals are in this expression, can you break them down or not? If you can break them down further, then they're not simplified. If you can't break them down anymore, then they're simplified. There are no radicands can contain fractions. So are there fractions within the radicals? If there are, we need to get rid of them. This relates to the third one, which is no radicals appear in the denominator of a fraction. That's where rationalizing comes in. That's what we're talking about here. So it depends on the scenario. But either way, it's going to involve, in order to rationalize the denominator, it's going to involve multiplying both the numerator and denominator by something that is going to create a perfect nth power of the denominator. I know that's a lot of words. Let's see this in action. Okay, so before we actually see the rationalizing in action, we're going to touch on the first one here. So no radicands have perfect nth powers as factors other than 1. So here I have the cube root of 135. So what I want to always try and do, and again, we've seen this a lot with square roots, but now we're seeing it with more other types of roots as well. So I want to think about, since I have a cube root, I want to think about my perfect cubes, which are 1, and 2 cubed is 8, and 3 cubed is 27, and 4 cubed is 64, and 5 cubed is 125. And I know since this is 135, I definitely don't need to even worry about 125. So what I would do at this point is I would literally do guess and check on my calculator, and I would see, is 135 divisible by any of those perfect cubes? So let's do 135 divided by 64. I know that's not going to work because it had an end of 5, but I'm just showing you the guess and check part. So let's do 135 divided by 27. And ideally, we want to find the largest one, right? Just anytime we want to break down roots. So I'm going from largest to smallest. Boom. Oh my God. 135 divided by 27 is 5. Solid. So what I'm going to do then is I'm going to think of this, or actually I'm going to rewrite it as the cube root of 27 times 5. And remember from our properties of radicals, I can think of this as the cube root of 27 times the cube root of 5. But I know that the cube root of 27 is 3, so this becomes 3 cube root of 5. Nice. Okay, so now let's do a rationalizing problem. So let's look at B. I have root 11 over root 5. And now again, I'm just going to go back here because I'm not trying to confuse you, but I want to talk about what this actually meant. So we want to multiply the numerator and denominator by something that will create a perfect nth power of the denominator. So this is a square root, so I'm trying to get the denominator to be a perfect square. So what is 5 squared? Well, that's 25. What can I multiply 5 by to make it 25? I would multiply it by 5. However, this is in a root, so I need to multiply it by root 5. So I'm going to multiply the numerator and denominator, because that's the same as multiplying by 1 then, right? So that's the algebra part of it. But I'm choosing to multiply by root 5 because I know that's going to create root 55 over root 25. And root 25 is 5. So I end up with root 55 over 5. Any questions? Okay. And so that was rationalizing because now the root is not in the denominator. I would also want to check, does the numerator reduce at all? It doesn't, because I know the factors of 55 are 11 and 5. Both those are prime. Okay, I want you to do C. Pause the video, rationalize the denominator, unpause when you are ready to check. Hint, don't forget to simplify as well. All right, so here I actually want to show you two ways to do this problem. So the first one is just starting out the same way I did for B, where I recognize the denominator is 8, so I know if I multiply by root 8, that will create a perfect square since it's a square root. I multiply the numerator and denominator by root 8. So that made the numerator root 56, because 7 times 8 is 56, and the denominator root 64. Root 64 is my perfect square of 8. However, I noticed that root 56, or 56 specifically, has a factor that is a perfect square. And so root 56 can be split up into 4 times 14, where 4 is a perfect square. So this becomes then 2 root 14 over 8. The 2 and the 8 reduce, and I end up with root 14 over 4. So this is my final answer. Now, another way I could have done this is I could have recognized from the beginning root 8 simplifies, right? I can think of root 8 as root 4 times root 2, which is 2 root 2. And so that's what I'm showing you over here is if before I rationalize, I actually simplify the denominator, I can rewrite the original expression as root 7 over 2 root 2, and now I would multiply the numerator and denominator by root 2, because that will create a perfect square here. So then I get root 14 over 2 root 4. Root 4 is 2, so it's root 14 over 2 times 2, which is root 14 over 4. Either way is correct. We get to the same result in the end. It's up to you on how you prefer to do it. Okay, so our last thing with rationalizing is what if the denominator is a little more complicated than just a single root? Okay, well, if we have a binomial, then we're going to multiply by the conjugate. We've talked about conjugates before as well. These came up with complex numbers and complex roots and irrational roots. So remember, a conjugate of a binomial is the same binomial but with an opposite middle sign. So for instance, the conjugate for a 5 plus root 3 is going to be 5 minus root 3. The conjugate for 3 minus root 2 is going to be 3 plus root 2. And the conjugate for root 7 plus root 3, well, I'm going to leave that for you to try on your own. But what we're going to do is we're going to multiply the numerator and the denominator by the conjugate. Now, when I multiply the numerator for the first one here, I have 1 times 5 and 1 times negative root 3 just stays 5 minus root 3. But in the denominator, we have to distribute. And notice what's going to happen, and this is why we multiply by the conjugate. 5 times 5 is going to be 25. 5 times negative root 3 is minus 5 root 3. 5 times root 3 is plus 5 root 3. And root 3 times negative root 3 is minus root 9. So the reason why we're multiplying by the conjugate is because if we've done this correctly, these middle terms should always cancel. And that means that our roots are gone because the last term, root 9, is actually just 3. So now I'm left with 5 minus root 3 in the numerator, and then the denominator is 25 minus 3. 25 minus 3 is 22. All right, I want you to try to do the last two. So try to do this one and this one. Pause the video, unpause when you're ready to check. All right, so for here, we already talked about the conjugate is 3 plus root 2. In this case, I need to distribute that root 6, right? So 3 times root 6 is 3 root 6. Root 6 times root 2 is root 12. And then in the denominator, 3 times 3 is 9. 3 times root 2 is 3 root 2. 3 times negative root 2 is minus 3 root 2. Negative root 2 times root 2 is minus root 4. So then a couple things need to happen. Again, these are going to cancel here and here. And then root 4 is 2, so 9 minus 2 gives me 7. And also notice that I broke down the root 12, right? The root 12 became 2 root 3, because root 12 is 4 times 3, or 12 is 4 times 3. Okay, then on the bottom one, so here the conjugate, I hadn't told you, but if you followed what we had done on everything else, hopefully you got this, was root 7 minus root 3. So I multiply the numerator and denominator by root 7 minus root 3, because remember, it's the same binomial, but an opposite middle sign. So I'm going to distribute the negative 1 in the numerator. Negative 1 times root 7 is negative root 7 times positive root 3, or plus positive root 3. Root 7 times root 7 is root 49. Root 7 times negative root 3 is minus root 21. Root 7 times positive root 3 is plus root 21. And then root 3 times negative root 3 is minus root 9. Again, these hopefully cancel, and in this case they do. So the numerator was minus root 7 plus root 3. I cannot combine those because they aren't the same root, or they're the same index, but the number underneath the root is not the same. Root 49 is 7, root 9 is 3, 7 minus 3 is 4. Boom, there is my answer. Nice work, guys. Okay, so make sure you understand how to rationalize a denominator, whether that is a binomial or whether it is just a single radical. Nice work.